Hello everyone. Today, I, Abhishek Jha, am going to present the paper titled Comparative Analysis of SOI Bulk Rectangular and Nanowire Optical Waveguide for Label-Free Lung Cancer Detection. This paper was written by me, Abhishek Jha, my batchmate Abhishek Kumar, under the guidance of our professor, Dr. Rituraj Singh. Now, here's the content slide, which is basically a summary of everything that I'm going to present today. And in short, is also a summary of the work that we have done so far. Now, moving on to our topic, that is lung cancer, let me introduce you to what lung cancer actually is. Lung cancer is a malignant lung tumor characterized by uncontrolled cell growth in tissues of the lungs. This growth can spread beyond the lung into nearby tissue or other parts of the body by the process of metastasis. Now let us further know what are the factors causing lung cancer. Smoking, secondhand smoke, family history, harmful infection, and air pollution are one of the major contributors to the cause of lung cancer. This list is not exhaustive and there can be many other factors, but these are some of the major ones. Now moving on to the symptoms of lung cancer. Number one, facial or neck swelling. Number two, chest pain. Number three, coughing of blood. Number four, weight loss. Number five, loss of appetite. Number six, trouble breathing. There can be other symptoms as well. And again, this list is also not exhaustive, but these are some of the major symptoms. Now, moving on to the types of lung cancer. Well, broadly, there are two types of lung cancer. They are non-small cell lung cancer, that is NSCLC, and small cell lung cancer, that is SCLC. Now, let us know a little bit about non-small cell lung cancer, that is NSCLC. About 80 to 85% of lung cancers are NSCLC. NSCLC consists of different types of lung cancers, which start from different types of lung cells. They are grouped together because the treatment and prognosis are often similar. The main subtypes of NSCLC are adenocarcinoma, squamous cell carcinoma, and large cell carcinoma. And here I have written a bit about each of the subtypes, giving us an overview of all of them. Now, moving on to small cell lung cancer, that is SCLC. About 10 to 15% of all lung cancers are SCLC. It is also known as oat cell cancer. This type of lung cancer tends to grow and spread faster than NSCLC. About 70% of people with SCLC will have cancer that has already spread at the time they are diagnosed. Since this cancer grows quickly, it tends to respond well to chemotherapy and radiation therapy. Unfortunately, for most people, the cancer will return at some point. Now, let us focus on some of the stages of non-small cell lung cancer. When the first stage is, the cancer is located only in the lungs and has not spread to any lymph nodes. Now, stage two, the cancer is in the lung and nearby lymph nodes. During stage three, which gets counted in one of the advanced stages, the cancer is found in the lung and in the lymph nodes in the middle of the chest. And during the fourth and final stage, the NSCLC has spread to other lung, the fluid around the lungs, the heart, or to distant lymph nodes or organs. Now, since we have some idea about the disease and its various types and its symptoms, now let me tell you something about our research. Well, over the past few years, there has been a steady rise in the use of optical biosensors for the diagnosis and detection of various target biomolecules. An optical biosensor is a compact analytical device containing a biorecognition sensing element integrated with an optical transducer system. The basic objective of an optical biosensor is to produce a signal which is proportionate to the concentration of a measured substance, that is the analyte, And in our case, the analyte will be the lung cancer cells. There are broadly two types, label-based biosensors and label-free biosensors. Label-based biosensors make use of labels like radioactive molecules, enzymes, fluorescent molecules, etc. that combine to the targeted analyte. Thus, the number of target molecules in the tested sample is found by measuring the label count and arriving at the corresponding value. This is usually done when the targeted analytes are hard to detect on the basis of their intrinsic physical properties. However, its major drawbacks are that the process is usually more costly, time consuming, and labeling the biomolecules can alter the binding properties of the analyte. Now coming to label-free biosensors. Label-free biosensors do not use labels to measure the presence of biomolecules and instead rely directly on the intrinsic physical properties of analytes for detection. Apart from giving real-time results, label-free biosensor has the added advantage of being cost-effective. And due to these advantages, we also are using label-free biosensors. Now, here's an overview of the previous work done and what we are going to do. It is an overview in a very crisp and nutshell manner. And first of all, a refractive index-based passive sensing technique where the waveguide is designed using a SiO2 substrate and Si nanowires with aqueous solution as the cladding is used by the sensor. The biosensor basically works by measuring the variation in the effective refractive index with variation in the width of the functionalization layer, which occurs when it thickens due to binding between the functionalization layer and corresponding biomarker for the lung cancer in human serum. Here, the existing work on silicon nanowire waveguide based label-free sensing of lung cancer is compared with well-known bulk rectangular optical waveguide. And of course, for illustrative purposes, we have kept the material and the physical parameters same in both the cases. It is determined that whether a bulk rectangular waveguide and a nanowire waveguide are suitable devices for detecting the presence of target biomolecules or not. The effects of change in the functionalization layer covering our study for the nanowire waveguide. This is what the later part of our experiment is. The change in containment factor and more effective refractive index with respect to change in functionalization layer coverage is studied. Now, coming to the design configuration of our waveguide. Here you can see on the left, there is bulk silicon rectangular waveguide, and on the right, there is silicon nanowire optical rectangular waveguide. You notice that in both the cases, we have kept the dimensions almost same for analogous things so that the comparison becomes easy. In both cases, the waveguide consists of silicon, then SiO2 substrate, and an aqueous solution. The height of the silicon rod is 220 nanometers. That is HS equals to 220 nanometers in both cases actually. And the width of the waveguide is 755 nanometers. And the height and width of the substrate are 500 nanometers and 1255 nanometers respectively. Now, this is the overall design of our waveguides without the functionalization layer. And this part of the experiment has been done without the functionalization layer to get an idea of the basic characteristics of the two waveguides so that we can later compare it with the corresponding ones with the functionalization. The first one here is transverse electric mode. In this mode, the electric field is purely transverse to the direction of propagation, whereas the magnetic field is not. Thus, Ez equals to 0 and Hz is not equal to 0. Here, in all the cases, Z has been considered as the direction of propagation, as is the convention. Next, moving on to transverse magnetic wave. In this mode, the magnetic field is purely transverse to the direction of propagation, whereas the electric field is not. That is, Ez not equal to 0 and Hz equal to 0. Next, in transverse electromagnetic wave, both the electric and magnetic field are purely transverse to the direction of propagation. There is no component in the Z direction, that is the direction of propagation. Thus, Ez equals to 0 and Hz equals to 0. And in case of hybrid modes, Neither the electric field nor the magnetic field is purely transverse to the direction of propagation. Thus, neither Ez equals to 0 nor Hz equals to 0. Now, since we have recapitulated what modes of propagation are, let us move on to mode investigation. Now, first talking about the rectangular waveguide, that is the bulk rectangular waveguide. Here, the field components of the waveguide along each of the directions for both electric and magnetic field are given. Here in the first row, you can see that the electric field has high intensity value inside the waveguide in the desired region along the x direction. But unfortunately, that is not the case along y and z direction. In both cases, the high intensity is not inside the waveguide and definitely not in the desired region. And in case of magnetic field, along the y direction, there is high intensity at the center of the waveguide, and which is also the desired region. But that is not the case for Hx and Hz. From this, we can conclude that the mode of propagation is positive. Now, moving on, by taking on the product of Ex and Hy, we can find the mode field intensity distribution of bulk rectangular waveguide, which has been displayed on the left. Here you will see that the intensity is high at the center of the waveguide, which is also the desired region. Now, moving to silicon nanowire rectangular optical waveguide, or SNROW. Here again, similar modal analysis has been done, and in the first row, for the fields, you can see that in the x direction, the electric field has high intensity values in the regions between the silicon nanowires. And from these, we can conclude that again here the mode is positive mode. Here you can see regions of high intensity between the silicon nanowires and regions of low intensity everywhere else and inside the silicon nanowires. So this region of high intensity between the silicon nanowires indicates that the power is flowing through between the gaps, which is something characteristic of a slot waveguide, which it looks like. And upon taking on the pointer vector distribution versus the x-cut coordinate, we see that a graph has been obtained in the shape of a Gaussian curve. Unlike a Gaussian curve, it is not smooth. There are bars and that indicate regions of highs and lows for the pointing vector value. These bars are there because of boundary changes. We see that the boundary here changes multiple times, and thus the physical properties like refractive index also change, like from silicon wire to upon going from silicon wire to the aqueous solution, and from going to the aqueous solution to the silicon wire. Thus, each of the bars here represent areas of high intensity. That is, this bar represents the area between the silicon nanowires, and these values indicate the region of the silicon nanowire where the intensity is low. So here also the graph keeps on rising, the bars keep on becoming more, as is logical because the highest intensity even inside the waveguide is at the center, but the envelope is rectangular. Thus we can say that overall it behaves as a rectangular waveguide. Now, moving on to sensing analysis. So in our previous experiments, we had not added the functionalization layer. Now we'll add a functionalization layer around both the bulk rectangle and the silicon nanowires, and the thickness of this functionalization layer will be 8 nanometers all around. Now you can see in the diagram what is being done. Now comparisons. Now we did similar experiments on both the waveguides with functionalization layer and compared them with each other and with the waveguides without the functionalization layer. And these comparisons gave us some significant insights. Now let's look into them. First, Comparison between mode field distribution of a bulk rectangular waveguide with functionalization layer and without functionalization layer. Here you can see that the distribution is almost the same. In fact, both are Gaussian shaped curves which overlap. This shows us that even after adding a functionalization layer, there is no change in the working of a bulk rectangular waveguide, and thus we unfortunately we cannot use bulk rectangular waveguide for detection of lung cancer cells. Now, moving on to the second one, that is the comparison between mode field distribution of SNORW with functionalization layer and without functionalization layer. Well, this one is a lot more interesting than the last one because this comparison gives us some of the biggest insights of our experiment. Here, the red dotted line shows the usual graph that we had seen earlier for the one without the functionalization layer. But it is interesting to note that for SNORW with functionalization layer, there are more sub-bars, there are more peaks than the one without the functionalization layer. Here we observe that the pointing vector rises in twice instead of once that was the case earlier. This pattern emerges in SNROW with functionalization layer because the boundaries change more times. Because after the addition of functionalization layer, the boundary changes from along the x-axis from going to from silicon to functionalization layer, from then again from functionalization layer to the aqueous solution, then from aqueous solution to again to the functionalization layer, and from functionalization layer again to the silicon nanowire. And thus, as with the change in material, there is a change in refractive index, and thus the propagation and the distribution of energy also changes, and thus one small bar upon each of the bars is there. But overall, you will see that the SNORW graph with functionalization layer is sort of like the one without functionalization layer in the sense that even this one has bars that is regions of high energy, and and this one also has an overall Gaussian shape, which indicates that overall it behaves like it propagates wave like a rectangular waveguide, and these small bars indicate that the energy also gets trapped inside the functionalization layer. Now, moving on to our next comparison, that is the comparison between mode field distribution of a bulk rectangular waveguide with functionalization layer S and SNORW with functionalization layer. Well, here you can see that this is a very basic comparison, and you can see that both of them have the same Gaussian shaped curve, and and another insight is that you can see that in this red graph, this is a smooth one, but in the second graph, that is the one with bars, you can see in some regions it is the energy is above the red graph, that is the rectangular waveguide, and in some regions the energy is below the rectangular waveguide. Thus, we can see that upon forming a slot waveguide sort of thing in the SNORW, what happens is that, like in the energy which should have been in the silicon nanowire region gets transferred to the energy between the silicon nanowire region, and thus the energy here gets transferred to this bar and this bar, and this is one of another things that we had observed. Now, moving on to comparative discussion. Well, this graph is actually the conclusion of the second part of our experiment, where we wanted to see that if there is any effect of functionalization-led coverage on the working of a silicon nanowire waveguide. So for this, we thought of seeing how the containment factor and the ineffective changes with change in the functionalization layer coverage. So initially the functionalization layer coverage was taken as 12 nanometers, and it was eventually increased stepwise to 228 nanometers. And the containment factor was particularly studied. Before we jump into interpreting this graph, let us see what containment factor is. Well, containment factor is nothing but the ratio of the power energy flowing through the desired region divided by the power energy that is flowing through the entire region. So here for describing the containment factor, we took the area between the silicon nanowires as our desired region, that is the numerator part, and the whole area of the waveguide as the complete the numerator part. And from this ratio, we obtain that the containment factor. And we can see that with increase in the effective functionalization layer coverage, the containment factor decreases. Well, what does that mean? That means that as the functionalization layer coverage was increased for the silicon nanowires, the energy between silicon nanowires decreased. And as we know that the energy does not go inside the silicon nanowires themselves, it indicates that the energy is getting transferred to the functionalization layer. And this is something good for us because in the end, it is the functionalization layer that is actually detecting our target molecules, that is the lung cancer cells. And thus, if there's less energy between silicon nanowires, it means that more energy is trapped in the functionalization layer, and this will help the functionalization layer perform better. Thus, we can see that with increase in functionalization layer coverage, the performance of the waveguide or optical biosensor is becoming better, and thus the silicon nanowire should be completely covered. Also, overall, the more effective refractive index is increasing. The results show that nanowire waveguides have high sensitivity for early detection of lung cancer, and the rectangular bulk waveguide fails to detect any lung cancer biomolecules. Both the electric and magnetic field distribution inside the rectangular as well as nanowire waveguide suggest that the mode present is POSI-PE. It was demonstrated that there was no change in the Poynting vector profile of the rectangular bulk waveguide even after adding the functionalization layer. Therefore, it can be concluded that the rectangular bulk waveguide is not suitable for an optical biosensor. The X-cut intensity pattern of the nanowire waveguide with functionalization layer has a completely different and non-overlapping pattern with the nanowire waveguide without the functionalization layer. The increase and decrease in the Poynting vector value at various places in the waveguide is due to changes in the refractive indices at the boundary of the two materials. These multiple changes suggest us that the functionalization layer of the nanowire waveguide creates a change in the energy distribution of the waveguide and thus can be used for the detection of biomolecules. More functionalization layer coverage leads to better detection. And these are the references that we had used. And a very thank you to all of you for being such patient and wonderful listeners. Thank you.